Welcome to the Deep Dive. Today we're tackling a truly revolutionary idea, something that really reshaped how we see our planet from the ground up, plate tectonics.
Absolutely. It's, on par with evolution in biology or relativity in physics, just a fundamental shift.
Yeah, a real paradigm shift like Thomas Kuhn talked about. You know how sometimes a single idea can just change everything?
That's exactly what happened here. For centuries, the continents were just assumed to be fixed, locked in place.
Right, immovable.
Then, early 20th century, Alfred Wegener comes along and proposes continental drift.
A pretty wild idea for the time. Continents moving.
Very bold. But, well, he lacked a solid mechanism. How did they move?
So people were skeptical.
Very. It was largely dismissed for decades. It just goes to show sometimes these huge ideas, they take a while to sink in for the mainstream scientific community. Lovelock had a quote about that, didn't he?
He did, about the time it takes. And it wasn't until the mid-1900s, really, with all this amazing new data from the ocean floor.
Magnetic stripes, yeah, and mapping those mid-ocean ridges.
Exactly. Suddenly, Wegener's core idea didn't seem so crazy.
And Harry Hess proposed seafloor spreading. That was a key piece.
The evidence just kept mounting. By the late 60s, maybe early 70s, the pieces clicked together for a whole community of scientists.
And boom, plate tectonics as we know it. The unifying theory for geology.
So that's our mission for this deep dive. We're going right into the chapter on plate tectonics from Earth, Portrait of a Planet, the 6th edition.
Yep. We'll unpack the core concepts, the processes, look at the diagrams, connect it to real places, maybe some geotours examples.
And explain the jargon simply. Show you how this theory makes sense of so much about Earth.
Okay, let's start with the absolute basics. The concept of a lithosphere plate.
Right. This is Earth's rigid outer shell. Think of it like the crust, the ground we walk on.
And crucially, the very top bit of the mantle, the layer just underneath the crust.
The key word being rigid.
Exactly. The lithosphere, when you push on it, it tends to bend, or if you push hard enough, break, like a sheet of ice over water.
Okay, and beneath that rigid lithosphere.
You have the asthenosphere, still part of the mantle, but it behaves totally differently.
How so?
It's plastic, it can flow. Think really, really thick honey or tar. It flows, but incredibly slowly.
So that contrast, rigid layer on top, flowing layer underneath, that's what allows the plates to move.
That's the fundamental idea, yes. The rigid plates are essentially floating and moving on this slowly flowing asthenosphere.
Now here's the thing that kind of surprised me. The lithospheric mantle and the asthenosphere, they're made of the same stuff.
Pretty much, yeah. The same ultramafic rock. The big difference isn't composition, it's temperature.
Oh, okay.
The lithospheric mantle is cooler below about 1280 degrees Celsius, which makes it rigid. The asthenosphere is hotter than that, which allows it to flow.
So that 1280 degrees C is the key boundary.
It's the critical temperature boundary, yes. But don't picture it as a sharp line, like a crack. It's more gradational.
Right, sort of a zone where things transition from rigid to flowy.
Exactly. As you go deeper, it gets hotter, and the rock's behavior changes gradually.
Okay, so we have these lithosphere plates. Are they all the same?
Not at all. There's a big difference between the plates that make up the continents and the plates under the oceans.
Let's start with thickness.
Okay. Continental lithosphere is much thicker. We're talking 150, maybe 200 kilometers deep.
Wow, okay. And oceanic.
Much thinner, especially where it's brand new. At the mid-ocean ridges, sometimes less than 10 kilometers thick there.
Less than 10. That's thin.
It thickens as it moves away and cools, though. Out in the deep ocean basins, the abyssal plains, it might reach about 100 kilometers thick. Still thinner than continental lithosphere.
And the crust itself, that very top layer, different too.
Oh, yeah. Continental crust, the land, is also thicker. Average may be 35 kilometers, but can be up to 70 kilometers under big mountain ranges. And it's made of lighter, less dense rocks like granite, felsic, and intermediate stuff.
Okay, lighter rocks and oceanic crust.
Thinner again, only about 7 to 10 kilometers thick. And it's made of denser rock, mostly basalt, mafic rock.
So thicker, lighter continents and thinner, denser ocean floors. Does that affect elevation?
Directly. Think about buoyancy. The thicker, less dense continental lithosphere essentially floats higher on the denser asthenosphere.
Like the book's analogy, a cork versus a piece of pine in water.
Exactly. The cork, continental crust, floats higher than the pine, oceanic crust, and both float on the water, asthenosphere. The oak block represents the denser lithospheric mantle underneath both.
Which explains why continents are generally higher than the ocean basins. It's this principle of isostasy, right? Things floating based on thickness and density.
Precisely. Isostasy. We'll probably touch on that again.
So Earth's lithosphere isn't just one solid piece. It's broken up.
Into about 20 distinct plates. Lithosphere plates are just plates.
And these vary in size.
Yep, there are major plates like the North American, the African, the Pacific plates, and then smaller ones, the microplates like the Cocos Plate or the Juan de Fuca Plate off the U.S. West Coast.
And some are purely oceanic, while others carry continents.
Correct. The Nazca Plate is entirely oceanic. The North American Plate carries the continent, but also a big chunk of the Atlantic Ocean floor.
Okay, now you mentioned plate boundaries. What about the edges of continents that aren't plate boundaries?
Ah, good point. We distinguish between active margins, which are plate boundaries. Think the west coast of South America with the Andes.
Lots earthquakes and volcanoes there.
Exactly. And then passive margins, which are not plate boundaries. They're just the transition from continental crust to oceanic crust within the same plate.
Like the east coast of the U.S.
Perfect example. It's tectonically quiet. What you typically find there is older continental crust buried under a thick wedge of younger sediments washed off the continent over millions of years.
Forming a passive margin basin.
Right. And the shallow underwater part of that sediment pile, that's the continental shelf, usually less than 500 meters deep.
Home to important fisheries.
Often, yes.
Okay, let's quickly summarize the core principles of plate tectonics then.
Sure. 1. The lithosphere is divided into these plates, and they move.
2. Most of the action, the slipping, grinding, separating, happens at the boundaries between plates. The insides of the plates are mostly rigid.
3. Continents don't plow through the ocean floor. They're embedded in the plates and move with them. That's Wegener's drift explained.
And 4. Because of all this, the map of Earth's surface isn't static. It's constantly changing over geologic time.
That's the essence of it.
So how do we actually know where these plate boundaries are located?
Earthquakes are the key. If you plot the locations of earthquakes worldwide.
They're not random at all, are they?
Not at all. They fall into distinct narrow bands. Seismic belts.
And earthquakes are basically vibrations from rocks breaking and sliding along faults deep underground.
Exactly. The point where the break starts is the focus. And the point on the surface directly above is the epicenter.
And these seismic belts, they pretty much perfectly trace the edges of the tectonic plates.
They do. It makes sense, right? The boundaries are where plates are interacting, pulling apart, pushing together, sliding past. That's where the stress builds up and causes rocks to fracture and slip.
While the interiors of the plates are relatively quiet, earthquake-wise.
But it's quieter because they're not experiencing that intense boundary interaction.
Okay, so based on how the plates move relative to each other at these boundaries, we can classify them.
Into 3 main types, yes. You've got divergent boundaries, where plates move apart.
Spreading centers.
Convergent boundaries, where plates move towards each other, and usually one sinks beneath the other.
Subduction zones.
And transform boundaries, where plates slide horizontally past one another.
Like the San Andreas fault.
Exactly. And each type has its own characteristic set of geological features.
Let's dive into divergent boundaries first. Spreading boundaries. This is where new ocean floor is made, right?
Mm-hmm.
At mid-ocean ridges.
Correct. The Mid-Atlantic Ridge is the classic example. It's this enormous underwater mountain range.
Running right down the middle of the Atlantic.
From near Greenland all the way south. It rises maybe 2 kilometers above the deep ocean floor, the abyssal plains, but its crest is still way underwater, maybe 2 to 2.5 kilometers deep.
And along the very center, the axis of the ridge, there's often a valley.
A median valley, yeah. Often a kilometer deep, a sort of trough. And that valley floor is where the new oceanic crust is actively forming.
With steep cliffs forming the valley walls.
Right, steep scarps. Then farther away, the slopes become gentler, leading down to those flat abyssal plains hundreds of kilometers from the ridge axis. The whole thing is remarkably symmetrical.
So how does this new crust actually form there? What's the process?
Okay, picture this. Deep beneath the ridge axis, hot, buoyant asthenosphere rock is slowly rising, maybe just centimeters per year.
Okay, slowly rising.
As it rises, the pressure drops, and that decrease in pressure allows it to undergo partial melting, maybe up to 15% melts, forming mafic magma, molten rock, but a bit richer in silica than the original mantle rock.
And this magma is less dense, so it wants to rise further.
Exactly. It's buoyant. Some of it collects in a magma chamber, maybe 2 to 7 kilometers beneath the seafloor. It's not a big open cavern of lava, more like a mush of crystals floating in melt.
A mushy magma chamber.
Yeah. As this chamber cools along its sides, some magma solidifies slowly to form a coarse-grained rock called gabbro.
Okay, gabbro deeper down. What about closer to the surface?
Some magma keeps rising, injecting into vertical cracks above the chamber. When it cools and solidifies in these cracks, it forms sheet-like intrusions called basalt dikes.
Like walls of solidified magma.
Exactly. And then if the magma makes it all the way to the seafloor and erupts...
Underwater lava flows.
Right. But because it erupts into cold seawater, it cools incredibly quickly, forming these characteristic rounded, blobby shapes called pillow basalt. Often meter-wide pillows.
So you get layers, pillow basalt on top, basalt dikes underneath, and then gabbro at the base. That's the structure of new oceanic crust.
That's the classic three-layer model, yes.
And people have actually seen this environment up close.
Oh, yes. Research submersibles have explored parts of the mid-ocean ridges. They've seen submarine volcanoes erupting, pillow lavas forming.
And those black smokers you mentioned.
Black smokers, yes. These hydrothermal vents along the ridge axis, seawater seeps down through cracks, gets superheated by the magma below, dissolves minerals from the hot rock.
And then shoots back out.
Shoots back out into the cold ocean water. When the hot, mineral-rich water hits the cold seawater, the dissolved minerals suddenly precipitate out, forming these dark, chimney-like structures, and the smoke actually fine mineral particles.
Fascinating. And life thrives there.
Amazingly, yes. Unique ecosystems based on chemosynthesis, using the chemicals from the vents. Bacteria, strange shrimp, tube worms. It's a whole different world down there.
So this whole process, new crust forms at the axis, then moves away.
That's seafloor spreading. Like a giant conveyor belt. New seafloor is made at the ridge, then travels laterally away.
Which means the youngest seafloor is right at the ridge crest.
Always. And it gets progressively older as you move away. Out near the continents, flanking the Atlantic, you find the oldest crust formed when the ocean first started opening.
And the oldest known ocean floor is somewhere in the Pacific, about 200 million years old.
Roughly, yes,
Yeah.
in the Western Pacific. Because ocean floor eventually gets destroyed at convergent boundaries.
We'll get to that. But back at the ridge, all this pulling apart must cause earthquakes too.
It does. The tension breaks the newly formed crust, creating normal faults. Slip on these faults generates the earthquakes commonly found right at the ridge axis and contributes to forming those steep scarps bordering the median valley.
Okay, that covers the crust. What about the rest of the oceanic lithosphere, that rigid mantle part underneath? How does that form?
Good question. Right at the ridge axis, it's too hot. Temperatures are near that 1280 degrees C boundary, even at the base of the new crust. So effectively, there's no lithospheric mantle right there.
It's all asthenosphere underneath the thin crust.
Pretty much. But as that new oceanic crust moves away from the ridge, it cools down. And importantly, the uppermost mantle rock directly beneath it also cools down, losing heat to the ocean above.
So as that mantle cools below 1280 degrees C.
It becomes rigid. It transforms from asthenosphere to lithosphere. So the lithospheric mantle layer essentially grows from the bottom down as the plate ages and moves away from the ridge.
Meaning the entire oceanic lithosphere plate gets thicker with age and distance from the ridge.
Exactly. The crustal thickness stays pretty constant once it's formed, but the underlying lithospheric mantle thickens as it cools.
Does it thicken indefinitely?
No, the rate of cooling and thickening slows down over time. It reaches a maximum thickness around maybe 80 million years old.
And because it's cooling, it's also becoming denser.
Yes. Cooler rock is denser, so older oceanic lithosphere is thicker and denser than younger lithosphere.
And denser things sink lower.
Right, like adding ballast to a ship.
Yeah.
The older, denser oceanic lithosphere sinks deeper into the underlying, slightly less dense asthenosphere.
Which is why the deep ocean basins, the abyssal plains over the old seafloor, are much deeper than the younger, hotter, more buoyant mid-ocean ridges.
Precisely. It all fits together.
Okay, let's switch tracks now to convergent boundaries. Plates moving towards each other.
Right. And at least one of the plates involved has to be oceanic lithosphere.
Why is that?
Because the key process here is subduction. One plate bends and sinks down into the asthenosphere beneath the other plate, and only dense oceanic lithosphere can really do that effectively.
Okay, so one plate dives under the other.
Exactly,
Yeah.
That's subduction. Because old oceanic lithosphere is being consumed or recycled back into the mantle here, these are also called consuming boundaries.
And they create those really deep parts of the ocean.
Yes, the deep ocean trenches. They mark the place where the plate starts its downward bend.
Is the rate of consumption here balanced by the creation at divergent boundaries?
Roughly, yes. Over geologic time, the amount of seafloor created at ridges is approximately equal to the amount destroyed at trenches, so Earth's surface area stays pretty much constant.
Why does the oceanic plate sink? Just because it's moving towards the other plate.
Not just that, once oceanic lithosphere gets older than about 10 million years, it has cooled enough and become dense enough that it's actually denser than the hot asthenosphere below it.
So it sinks under its own weight, like an anchor.
That's a great analogy. It becomes negatively buoyant and wants to sink. However,
It doesn't just plummet straight down.
no, because the asthenosphere, while it flows, is incredibly viscous. It resists that sinking motion. So the subduction happens relatively slowly, less than about 15 centimeters per year, usually slower. That viscosity is also why the main horizontal part of the plate doesn't just sink.
It needs that downward band of the trench to get started. Okay, so the downgoing plate must be oceanic lithosphere. What about the overriding plate?
That can be either oceanic or continental.
Why doesn't continental lithosphere subduct?
It's all about buoyancy again. Continental crust is thick, yes, but it's made of those lighter, less dense felsic and intermediate rocks. It's just too buoyant to be forced down deep into the dense mantle.
Like trying to sink a life preserver.
Exactly. It might get dragged down a little bit in a collision, but it won't subduct significantly. That's why continental crust is so old, it doesn't get recycled like oceanic crust. Some continental rocks are over 3.8 billion years old.
Wow. Okay, so convergent boundaries, lots of action. Earthquakes.
Big time. As the downgoing plate scrapes against the base of the overriding plate, you get massive earthquakes near the surface. These can be devastating for coastal cities.
But earthquakes happen deeper, too.
Yes, within the sinking slab itself. As it bends and descends, it continues to fracture, generating earthquakes down to depths of about 660 kilometers.
And this pattern of earthquakes traces the path of the sinking plate.
Perfectly. It forms an inclined band of seismicity called the Wadati-Benioff zone, named after the scientists who discovered it.
Why does the earthquake stop around 660 kilometers?
That depth marks a major transition zone in the mantle. Below that, the physical conditions change, and perhaps the slab becomes too ductile or undergoes mineral changes that prevent brittle failure, which is needed for earthquakes.
But the slab might keep sinking deeper.
Oh yes, seismic imaging suggests slabs can penetrate deep into the lower mantle, maybe accumulating in a kind of slab graveyard down there.
Okay, what other geological features do we see at convergent boundaries, besides the trench?
Well, as the downgoing plate subducts, sediment sitting on top of it, mud, clay, tiny plankton shells get scraped off.
Like snow piling up in front of a plow.
Exactly. This scraped off sediment, plus maybe some sand washed in from nearby land, accumulates in a wedge-shaped mass called an accretionary prism. It gets incredibly deformed, squashed, and contorted.
Okay, accretionary prism. Anything else between that and the volcanoes?
Sometimes, behind the prism, you get a depression called a forearc basin, where more sediment can collect, usually eroded from the land mass or volcanic arc nearby.
And then the volcanoes, the volcanic arc.
Right. A chain of volcanoes typically forms on the overriding plate, parallel to the trench, sitting behind the accretionary prism and forearc basin.
How do they form? Where does the magma come from?
It comes from the mantle above the sinking plate. As the downgoing oceanic slab reaches a depth of around 100 to 150 kilometers, heat and pressure cause it to release water and other volatile fluids that were trapped in its minerals.
Okay, water is released.
This water rises into the wedge of hot asthenosphere mantle sitting above the slab. Water dramatically lowers the melting point of mantle rock.
So the mantle wedge starts to melt, even though the temperature hasn't necessarily increased.
Exactly. It's called flux melting. This generates magma, which is less dense and rises to the surface to feed the volcanoes in the arc.
And if the overriding plate is a continent?
You get a continental volcanic arc, like the Andes in South America. The volcanoes are built on the edge of the continent. Sometimes the compression associated with the convergence also causes faulting and mountain building behind the arc itself.
And if the overriding plate is also oceanic?
Then you get a volcanic island arc, a chain of volcanic islets built on the overriding oceanic plate. Japan, the Aleutian Islands, the Marianas, those are all island arcs.
And sometimes you get a small sea behind the island arc.
Yes, a marginal sea, or sometimes called a back arc basin. These can form in a couple of ways. Maybe subduction started offshore, trapping older oceanic crust behind the arc, or maybe stretching and thinning of the overriding plate behind the arc leads to seafloor spreading on a smaller scale back there.
Lots going on at convergent boundaries.
Definitely the most complex type of boundary in many ways.
Okay, third type, transform boundaries. You mentioned the San Andreas fault. How are these discovered in the oceans?
Through detailed mapping of the mid-ocean ridges, scientists saw that the ridges weren't continuous lines. They were broken into segments, offset from each other.
Offset along these things called fracture zones.
Exactly. Fracture zones are these long, narrow belts of rough seafloor, kind of like linear valleys and ridges, that intersect the ridge segments at roughly right angles and extend outwards for hundreds, even thousands of kilometers across the abyssal plains.
And initially, people thought the entire fracture zone was a fault causing the offset.
That was the initial assumption, yes, that the entire length was actively slipping, like a giant strike-slip fault.
But earthquake data showed something different.
It did. When they precisely located the earthquake epicenters, they found that earthquakes only occurred on the segment of the fracture zone that lies between the ends of the two offset ridge segments.
Not on the parts extending further out.
Correct. The portions of the fracture zones extending away from the ridge crest out into the abyssal plains were seismically inactive, no earthquakes.
So what was going on?
J. Tuzo Wilson, a Canadian geophysicist, figured it out in the context of seafloor spreading. He realized the fracture zones form at the same time as the ridge segments. The ridge axis itself was segmented from the start.
So the offset isn't caused by later faulting. It's built in.
Right. And the active part of the fracture zone, the part between the ridge crests, is where the plates are moving in opposite directions, sliding past each other.
Consistent with seafloor spreading away from both ridge segments.
Exactly. But beyond the ridge segments, on the inactive parts of the fracture zone, the lithosphere on both sides is actually part of the same plate, or moving in the same direction. So there's no relative motion, hence no slip and no earthquakes.
So that active segment between the ridge ends is the transform boundary.
Precisely. That's the transform fault or transform boundary. It's the third type of plate boundary. Plates slide horizontally past each other along, typically a vertical fault.
And importantly, no new plate is formed and no old plate is consumed.
Correct. Lithosphere is conserved, it's just sideways motion.
Do all transform faults link mid-ocean ridge segments?
Most do, but not all. Some can link a ridge segment to a trench or two trenches together, and as we said, some cut across continents.
Like the San Andreas in California.
Yes, that's probably the most famous continental transform fault. It's part of the boundary between the Pacific Plate and the North American Plate.
Which way are they moving?
The Pacific Plate is moving northwest relative to the North American Plate. The fault connects a spreading center in the Gulf of California to the south with technically a complex area involving a trench and another transform fault system to the north, off the coast of Oregon and Washington.
Okay, makes sense. Now, are there places where these different boundary types meet?
Yes, absolutely. Points where three plate boundaries intersect are called triple junctions.
Triple junction. Makes sense.
They're named based on the types of boundaries that meet there. For instance, there's a ridge-ridge triple junction in the Indian Ocean.
Okay.
North of San Francisco, near Cape Mendocino, there's a trench transform triple junction where the San Andreas fault meets the Cascadia subduction zone and the Mendocino fracture zone transform.
So complex meeting points.
Yeah.
What about volcanoes that aren't on plate boundaries? You mentioned hotspots earlier.
Right. So we have volcanoes at divergent boundaries, mid-ocean ridges, and convergent boundaries, volcanic arcs. But then there are these other volcanoes, often isolated or in chains, that pop up far from any plate edge.
Hawaii being the classic example. It's thousands of kilometers from the nearest plate boundary.
Exactly. Hawaii, Yellowstone, Iceland, though Iceland is also on a ridge, Reunion Island. There are about 100 or so identified hotspots around the world. Some are in the middle of plates, some happen to lie on ridges.
And Tuzo Wilson noticed something about the chains associated with some hotspots.
Yes, he saw that often the active volcanism is concentrated at one end of a chain of inactive, older volcanic islands and seamounts, which are underwater volcanoes, like the Hawaiian chain.
Unlike a volcanic arc, where volcanoes can be active all along the chain.
Right. So Wilson proposed that these hotspot volcanoes form above a localized, relatively stationary heat source deep in the mantle. The plate moves over this fixed source.
Like paper moving over a candle flame.
Sort of. The active volcano is currently over the heat source. As the plate moves, the volcano gets carried away, becomes inactive, starts to erode and sink, and a new volcano forms over the stationary source,
Creating the chain over time.
creating the hotspot track.
What's the source of the heat? The current thinking involves mantle plumes.
That's the favored model, yes.
Ah.
Mantle plumes. The idea is that these are columns of exceptionally hot and therefore buoyant rock rising slowly from deep within the mantle, maybe even from the core mantle boundary.
Rising up through the asthenosphere.
Right. When the hot plume head reaches the base of the relatively cool, rigid lithosphere, the decrease in pressure combined with the high temperature causes decompression melting.
Generating magma.
Exactly. Generating magma that then rises through the lithosphere to erupt at the surface, forming the hotspot volcano.
And the Hawaiian Emperor chain is a perfect example.
It really is. Active volcanoes on the big island of Hawaii at the southeast end, then progressively older, inactive, eroded islands like Maui, Oahu, Kauai to the northwest. And then the chain continues underwater as the Emperor seamounts, stretching much further northwest.
And there's a bend in that chain.
Yes, a prominent bend. The rocks at the bend are about 47 million years old. This tells us the direction of the Pacific Plate's motion changed around 47 million years ago. Hotspot tracks are amazing recorders of absolute plate motion.
And hotspots can occur under continents too, like Yellowstone.
Yes, Yellowstone's geysers, hot springs, and past massive volcanic eruptions are attributed to a continental hotspot. And as mentioned, Iceland sits atop both the mid-Atlantic ridge and a hotspot, which is why it's such a large volcanic island compared to the rest of the underwater ridge. The extra magma supply from the plume builds it up higher.
Okay, so plates move, boundaries exist. But how do these boundaries actually form? And can they disappear? The map isn't permanent, right?
Definitely not permanent. The configuration of plates and boundaries changes dramatically over geologic time. New divergent boundaries can form when continents split apart.
This is continental rifting.
Continental rifting, yes. It's the process where continental lithosphere stretches horizontally and thins vertically.
What happens when it stretches?
In the upper crust, which is cold and brittle, stretching causes rocks to break along faults. Blocks of crust drop down, creating a linear depression called a rift valley. This valley often starts filling with sediment.
And deeper down, where it's hotter?
Deeper down, the stretching happens more like pulling taffy. It's ductile deformation. The whole lithosphere thins.
And thinning the lithosphere lets the hot asthenosphere get closer to the surface.
Exactly. Hot asthenosphere rises to fill the space, and this can lead to melting and volcanic activity along the rift axis.
So you get faulting, valleys, volcanoes.
All characteristic of a continental rift zone. Now, if the rifting continues...
The continent breaks completely.
Yes. If stretching and thinning go far enough, the continent splits in two. A new mid-ocean ridge forms in the gap, seafloor spreading begins, and a new ocean basin is born.
And the edges of the original continent become
passive margins. Those thinned, faulted edges subside and get covered by sediment as the new ocean widens. Those triangular wedges you see in cross-sections of passive margins often represent the blocks faulted during the initial rifting phase.
Does rifting always succeed in splitting a continent?
No, sometimes it starts but then stops before full separation occurs. You end up with a failed rift, often marked by a thick accumulation of sediment in the old rift valley.
Are there active rifts today?
Oh, yes. The Basin and Range province in the western U.S. is a very wide zone of crustal extension and faulting.
Nevada, Utah, all those north-south mountain ranges and valleys.
That's the one. Then there's the East African Rift, a massive system stretching over 3,500 kilometers north-south. You get deep valleys bounded by huge fault cliffs and active volcanoes like Kilimanjaro.
Is that one succeeding?
It looks like it in places. It connects northwards into the Red Sea and the Gulf of Aden. Those are narrow, young oceans where rifting has succeeded, and seafloor spreading is occurring along newly formed mid-ocean ridges. The rift kind of dies out in the Gulf of Suez, though.
So rifts create divergent boundaries.
Yeah.
How do convergent boundaries die?
They typically end through collision.
Collision, like a car crash.
Sort of, but much slower. It happens when something buoyant, a continent, or maybe a volcanic island arc, gets carried into the subduction zone on the downgoing plate.
And it can't subduct, right? Too buoyant.
Exactly. It arrives at the trench and essentially jams the system. Subduction stops, or at least slows dramatically.
And the two buoyant pieces crumple together.
Yes. The classic example is India colliding with Asia.
Forming the Himalayas.
Precisely. For millions of years, the oceanic lithosphere between India and Asia was subducting under Asia. India moved steadily northwards. Around 40–50 million years ago, the continent of India arrived at the trench.
And couldn't sink.
Right. It could only slide under Asia a little bit before the buoyancy really resisted further subduction. But the plate convergence continued, so the two continents got squeezed together with incredible force.
Pushing up the mountains.
Pushing up the Himalayas and the vast Tibetan plateau behind them. The The rocks and sediments caught between the colliding continents were faulted, and uplifted dramatically. The crust there thickened enormously, maybe 60, 70 kilometers thick under the Himalayas.
Wow. Is there a name for the boundary where they joined?
It's called a suture. Sometimes you can find slivers of the old oceanic crust that got trapped along the suture zone during the collision.
So collision involves any two buoyant pieces meeting at a convergent boundary.
Yes, could be continent-island arc, maybe even arc-arc, or collisions involving chunks of thickened oceanic crust called oceanic plateaus. The key is that something too buoyant arrives and chokes the subduction zone.
And the convergent boundary effectively dies.
It ceases to be an active subduction zone, yes. The collision creates a major mountain range instead. The Alps in Europe also formed from collisions. And even older eroded ranges like the Appalachians in North America record ancient collision events, including the one between Africa and North America that helped form the supercontinent Pangaea about 280 million years ago.
Okay, this leads to the big question. What actually makes these plates move? Mijin couldn't answer this.
Right. That was the big weakness in his original continental drift idea. For a long time, the prevailing thought was mantle convection simply dragged the plates along.
Like rafts on a river. Simple convection cells rising at ridges, sinking at trenches.
That was the early, simple model. Hot mantle rises, spreads sideways, cools, sinks, and pulls the overlying plate along.
But that model had problems.
It did. It's hard to reconcile simple, neat convection cells with the complex shapes and movements of the plates we actually observe. For instance, some plates are moving faster than the presumed convection currents below them, and the directions don't always match up.
So convection happens, but it's not the whole story.
Convection definitely happens. Heat needs to escape Earth's interior, so hot material rises, cool material sinks. And this mantle flow certainly influences plate motion. Seismic tomography gives us images of these broad upwelling and downwelling zones in the mantle.
And the flowing asthenosphere must exert some drag on the bottom of the plates.
It does exert shear, yes. Depending on the direction of flow relative to the plate motion, it might speed the plate up or slow it down. Some research suggests asthenospheric flow might push on sinking slabs or affect the angle at which they subduct, but it's not seen as the primary driver anymore.
What are the primary drivers then?
The plates themselves are now seen as active participants, not just passive passengers. Two major forces are considered crucial: ridge push and slab pull.
Ridge push, pushing away from the ridge.
Exactly. Mid-ocean ridges are elevated because the underlying lithosphere and asthenosphere are hot and buoyant. They stand higher than the older, colder, denser lithosphere of the abyssal plains further away.
Like a bulge in the middle of the ocean.
Right. Gravity acts on this elevated ridge, causing the lithosphere to effectively slide downhill away from the ridge axis. This exerts an outward-directed pushing force on the plate.
So the ridge doesn't actively push, gravity does. Like honey sliding down a slight tilt in a glass.
That's a good analogy. The upwelling asthenosphere beneath the ridge is more a consequence of the plates separating than the cause of the push. Ridge push is a gravitational sliding force.
Okay, what about slab pull?
Slab pull arises at subduction zones. Remember how old, cold oceanic lithosphere is denser than the asthenosphere?
Yes, so it wants to sink.
Right. Once a portion of the oceanic plate starts to sink down into the mantle at a trench, its sheer weight pulls the rest of the plate along behind it.
Like an anchor pulling its rope or chain down.
Exactly. The sinking slab is the anchor. Slab pull is now considered by most researchers to be the single most important driving force for plate motion, especially for plates that have significant amounts of old, dense oceanic lithosphere attached to subducting slabs.
Interesting. So ridge push helps get things started, but slab pull takes over as the main engine.
That's a common view, yes. Plates attached to sinking slabs tend to move faster.
How fast do they actually move?
We need to distinguish between relative plate velocity and absolute plate velocity.
Okay, what's the difference?
Relative velocity is the speed and direction of one plate moving compared to another plate. Absolute velocity is the speed and direction of a plate moving relative to a fixed point inside the Earth, like the deep mantle or the hot spots we assume are relatively fixed.
Like two cars on a highway. They have speeds relative to each other and speeds relative to a stationary tree on the side of the road.
Perfect analogy. The tree is the fixed reference point for absolute velocity.
How do we measure relative velocity?
The main way is using those marine magnetic anomalies, the stripes on the seafloor, parallel to mid-ocean ridges. We know the age of the magnetic reversals that created the stripes.
Right.
So we measure the distance from the ridge axis out to a stripe of a known age. Velocity equals distance divided by time, age. That gives the spreading rate on one side.
You double it for the full speed the two plates are moving apart.
If spreading is symmetrical, yes. That gives you the relative velocity between the two plates moving away from that ridge.
Okay, and absolute velocity. You mentioned hotspots.
Yes, if we assume hot spots are relatively fixed points in the mantle, then the track of volcanoes created as a plate moves over a hot spot records the plate's absolute motion.
Like the Hawaiian Emperor chain again.
Exactly. You measure the distance from the currently active volcano over the hot spot to an older volcano in the chain. You determine the age of that older volcano, maybe by radiometric dating.
And again, velocity is distance over time.
Right. Rate equals distance divided by age, and the orientation of the chain tells you the direction of movement. The bend in the Hawaiian Emperor chain shows the Pacific Plate changed direction about 47 million years ago.
So what are the typical speeds? Are we talking fast or slow?
Geologically fast, humanly slow. Typical rates are between 1 and 15 centimeters per year.
About the speed your fingernails grow.
That's the classic comparison, yes.
Can we actually see this movement happening now?
We can. That's the amazing thing about modern technology, specifically the Global Positioning System, GPS.
How does GPS help?
Scientists install extremely precise GPS receivers bolted permanently into the ground at various locations on different plates. These receivers continuously track their exact position via satellites.
And they can detect tiny movements.
They can detect displacements as small as 2 millimeters per year. Since plate motions are typically 5 to 75 times faster than that, GPS can directly measure plate movements over periods of just a few years.
Wow. So we can literally watch the continents move in real time.
Effectively, yes. Data from GPS networks confirms the velocities calculated from magnetic anomalies and hotspot tracks. We can see Southern California west of the San Andreas fault moving northwest relative to North America at up to 6 centimeters per year. We can see Turkey moving west relative to Asia. It's the ultimate proof of plate tectonics in action.
It really ties everything together. That slow speed, centimeters per year, seems tiny.
But over geologic time, it adds up incredibly. 2.5 centimeters per year, that's 25 kilometers in a million years.
And 2,500 kilometers in 100 million years.
Exactly. That's continent scale movement. The Atlantic Ocean is about 4,500 kilometers wide now. It started opening around 180 million years ago when the supercontinent Pangaea began to break apart. The speeds work out perfectly.
It really underscores how much Earth's surface has changed, looking back at Pangaea breaking up over the last couple 100 million years.
It's a radical transformation, seeing those reconstructions of continents drifting, oceans opening and closing. It's amazing.
Say that brings us through the whole chapter, doesn't it?
I believe so. We've covered a lot of ground, metaphorically speaking.
Yeah, absolutely. We started with a basic concept, the lithosphere plates, how they differ, why they move. We looked at earthquakes as boundary markers, then dove into the three boundary types: divergent,
Mid-ocean ridges, seafloor spreading, black smokers,
convergent,
subduction trenches, Wadati-Benioff zones, volcanic arcs, accretionary prisms,
and transform.
fracture zones, transform faults like the San Andreas.
Then we looked at special cases like triple junctions and hotspots, mantle plumes, those volcanic chains.
And how boundaries form through rifting and die through collision, building mountains like the Himalayas.
We tackled the driving forces, ridge push, slab pull, the role of convection, and finally, how we measure the velocities, both relative and absolute, using magnetic stripes, hotspots, and now GPS.
It really feels like we've hit all the key points from the chapter.
Okay, great. So as we wrap up, it's just incredible to think about this constant, immense power reshaping our planet beneath our feet.
Absolutely. These slow, relentless geological processes are continuously sculpting our landscapes, driving earthquakes and volcanoes, and controlling the long-term evolution of continents and oceans. It's a dynamic Earth constantly in motion.